So let us now solve the exercises. The first exercise, which tells us to prove lemma 1211, has already been solved. In fact, it is that lemma where we reformulated convergence of sequences of real numbers entirely in terms of distance. And that time itself we discussed what to do to have a proof. So that's done. In exercise 2, we have to show that the real line with this metric is indeed a metric space. Now the individual parts of this solution have already been done. Okay, so they are already available with us. You just have to go back to where these things are available and assimilate them and make a solution. For that, see proposition 433 and the paragraph after remark 5411. You go back to these places and you will understand everything. So that means exercise 2 is also done for us. Next comes exercise 3. Okay, so let's see what it has. Exercise 3, we have a set X and we have a function D with domain the Cartesian product X times X and range the set of all non-negative real numbers. And with these two things, we have to then give an example of such a pair X comma D which obeys axioms B, C and D of definition 12.1.2. Definition 12.1.2 is the definition of a metric, but not axiom A. So that means we have to give an example of a set and a function D on that set of this type such that that function D, although it looks like a metric, but it will only satisfy positivity, symmetry and triangle inequality, but not the first axiom. So let's see the solution. There are other parts also. There are parts B, C and D which we will see. Well, let us first solve part A. So we take the singleton set consisting of 0 in place of X. That means the only relevant pair on which you have to define the function D for us now is 0, 0. And we define D there to have the value 1. So you can immediately see that axiom A fails. What is axiom A? Axiom A tells us that for any x belonging to our set, D of x comma x should be equal to 0. But that's not the case here. So axiom A fails. Axiom B is vacuously true. Axiom B is positivity. It tells us that for any two distinct points x and y from x, D of x comma y has to be a positive real number. We do not have distinct points here. That is why it is vacuously true. And also axioms C and D are trivially true. Axiom C is symmetry. D of x comma y should be equal to D of y comma x. Here both x and y are equal to 0. So actually not just the D values at x comma y and y comma x, here x comma y and y comma x themselves are just 0 comma 0. So obviously symmetry is true and triangle inequality is also equally easily true. Why? Because D of x comma z has to be less than or equal to D of x comma y plus D of y comma z, and all the D values here are 0. So 0 is obviously less than or equal to 0 plus 0, that's why. Next let us see part B. Next we have part B. In part B again another such pair has to be given, but this time axioms A, C and D have to be true but not axiom B. That means positivity should fail but the other axioms have to be true. The set this time we have taken to be this pair set consisting of the two elements 0 and 1. And the function we have defined to be constantly 0. at every pair of elements of x. At any x comma y, d has been defined to be equal to 0. So immediately axiom A is true, because axiom A tells us that when x and y are the same, then we should have d value 0. Here all the d values are 0. What about axiom C, symmetry? That is also true. D of x comma y should be equal to d of y comma x. Here all d values are equal, so in particular those d values are also equal. Triangle inequality is also true. Again, it is actually just like part A. In part A, the only relevant pair was 0, 0. In this case, there are pairs other than 0, 0, but the d value is just 0. So again, in triangle inequality, you have 0 less than or equal to 0 plus 0. So axiom D is true. Axiom B, of course, is false, because the d value of 1, 0, had axiom B been true, it should have been a positive real number. It is not, because all the d values are 0. So that's how we have part B. Next, let's see part C. In part C, again another such pair, but this time axioms A, B and D have to be true, not C. So symmetry should fail now. Our set is the same as the previous part, consisting of 0 and 1, but we define the function differently. D of 0, 0 and 1, 1 are both defined to be equal to 0. So this immediately tells us that axiom A is true. Next, additionally, d of 0, 1 is defined to be 2 and d of 1, 0 is defined to be equal to 1. So that tells us that axiom C is not true. Axiom B is true because for distinct pair of distinct elements, which in this case of course is 1 and 0, these are the two ways in which you can consider them, and the corresponding d values should be positive real numbers. Yes, they are positive real numbers, 2 and 1. So axiom B is true. And actually you can verify that the triangle inequality in this case is also true. Although it won't be really a one-line argument, if you want to show that axiom D is true, you have to consider some cases. It won't be very long, but you have to go through some cases. So that part I am leaving to you. Okay, you have to do it yourself. So that is part C. And finally, let's see part D. In part D, again another such pair, but this time the first three axioms should be true for the function D, but the last one, triangle inequality, should fail. So this time we have taken a little larger set consisting of 0, 1 and 2, because we want the triangle inequality to fail. So the definition of the function D is a little long because more points are involved. The beginning of the definition of course has these pairs 0, 0, 1, 1 and 2, 2. And at all of them D has been defined to have the value 0. So this part of the definition of the function D tells us that axiom A is true. Then we go to those pairs where x and y are not equal. At 0, 1 and 1, 0, the D values are both equal to 5. That's the definition. And at the remaining pairs 0, 2, 2, 0, 1, 2 and 2, 1, all the D values are defined to be equal to 1. So this second part of the definition actually tells us what? It tells us that if the two chosen points x and y are distinct, then the D values are positive real numbers. That's what axiom B tells us, right? Because it is positivity. That is the case here, because the two values that you will get in this part of the definition are 5 and 1, which are positive real numbers. So that's how axiom B is true. And C of course is also true, symmetry, because the way we have defined the function D, at 0, 1 and 1, 0 we have the same value. At 0, 2, 2, 0, 1, 2 and 2, 1 we have the same value. But triangle inequality fails because you can see here d of 1 comma 0 is 5, and 5 of course is greater than 1 plus 1. d of 1 comma 2 is 1 and d of 2 comma 0 is also 1. So triangle inequality demands that d of x comma z should be less than or equal to d of x comma y plus d of y comma z. But here you have got the opposite inequality. That is why axiom d fails for this function d, and that is the solution. Let us see another one. In this fourth exercise, we have to prove that the way we restricted a metric on a given metric space to one of its subsets actually produces a metric on that subset, and which turns that subset itself into a metric space, and we called it a subspace of the original metric space. In this, we have to prove that that is really a metric space. So let's see the solution. Actually it's quite easy, but anyway, let's see the details. The solution starts by considering the fact that y is a subset of x. Recall that the original metric space was x comma d. So because of this containment, the Cartesian product y times y will be a subset of x times x. Now since the original metric d was a function with domain x times x and y times y is a subset of that, so we can restrict the original metric to the subset y times y, and that way we will get this function. Range of course will remain the set of non-negative real numbers, and this is our usual notation for denoting the restriction of a function to a subset. We write the function followed by a vertical bar, then here as a suffix we write the subset. Okay, so this is a well-defined function, this restriction. So you now at least have a function whose domain is y times y and whose range is the set of non-negative real numbers. Now you can expect this, you can hope that this is also a metric on y, just like d is a metric on x. Is it? Let's see. So the first thing that we see is this, whether this is 0, where y is any point in y, because this is just the restriction of the original function d to y times y, and y comma y belongs to the Cartesian product y times y. So by definition of restriction, this is nothing but the d value of y comma y. Note also that y being a point of y is after all also a point of x. So this makes sense, and since our original d is a metric, so this is equal to 0. That means axiom A has been proven to be true for this new function. Next comes axiom B, that is positivity. Next, to verify positivity for our new function, we take two distinct points y1 and y2 in y. So then they are distinct points in x also. So the d value of y1 comma y2 is a positive real number. But by the definition of restriction, this is nothing but this. So that way the new function also satisfies positivity. Next comes symmetry. By now you have understood very well what I am going to write next, and you can also see why this is very easy. But anyway, let's complete the solution. So next comes symmetry. We have taken any two points y1 and y2 in y, this time not necessarily distinct, they may be the same point also, but then those points are in x as well. So the d values of y at y1 comma y2 and y2 comma y1 are equal. However, this d value is just this d value, and this d value is just this d value. So they are also equal, and that's how our new function satisfies symmetry. And finally, next comes triangle inequality. So for triangle inequality, we have taken 3 points y1, y2 and y3 in Y, not necessarily distinct, and we have straight away considered this value of the new function at y1 comma y3. By the definition of the new function, this is just the d value of y1 comma y3, and because d is the metric, it satisfies triangle inequality. So this is less than or equal to the d value at y1 comma y2 plus the d value at y2 comma y3, which themselves are equal to these new function values at those ordered pairs. So that way the new function also satisfies triangle inequality, and that is why it is a legitimate metric on the subset Y, and this pair is a metric space. So that's the solution. So you can note one thing, and actually I have already mentioned this before. Unlike this, it's a bit difficult for a subset of a group, for example, to be a subgroup. The conditions are more stringent. However, any subset of a metric space is a subspace with respect to the metric induced on it by the original metric. That is also not how subspaces of, say, vector spaces arise. Any subset of a vector space is not a subspace, but any subset of a metric space at least is a subspace in this way. So let me end the video here itself, and I think tomorrow we have number theory. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.